Hey Pre-Cal, welcome back. So in our last lesson, we did an introduction to a bunch of stuff related to probability, right? And there was a few things that I said that we were going to be coming back to in this lesson, and so we will be doing that. So you looked at sample spaces and events and determining the probability of equally likely and unequally likely events, and you began to look at this multiplication principle. And so we're going to be talking more about the multiplication principle of probability, conditional probability, which we actually talked about. These were like the givens, right? So the probability of A given B. So probability of A intersect B over the probability of B, right? And so like narrowing your focus. And we looked at a lot of this stuff visually through a Venn diagram, right? And so in this lesson, we're going to also look at some tree diagrams to help us to calculate probabilities and see that piece of it as well. So, multiplication principle of probability. If A and B are independent events, right? That was one of the things that I said we were going to be coming back to more in our next lesson. They're independent events. The probability of both occurring is the probability of A and B intersect B is going to be equal to the probability of A times the probability of B if they're independent events. So jar A has 40 black and 60 white marbles. Jar B has 20 white marbles and 5 black marbles. If you take a marble from each jar, what is the probability that both are black? Okay, so our two events, let's think about what they are, is taking a marble, I'm sorry, the two events. So if you take a marble from each jar, what's the probability? So that you get a black marble from jar A, and then the probability of getting a black marble from jar B. Okay, so jar A, let's think about that. There's 40 black out of a total of 100 times the probability of getting a black one from jar B. There are 5 out of 25. So that's going to give us, what is that, 1 zeros. This is 2/5. 1/5. So I've got 2 25ths. Right? They're independent events. Me picking one out of one doesn't impact me picking it out of another. The probability of a randomly selected customer ordering a Frosty. Oh, we talked about this. This is from last time. And the is 0.2. The probability of ordering a burger, we didn't have that, is 0.5. Assuming these events are independent, so one doesn't impact the other, what is the probability that a customer orders both? Well, 0.2 times 0.5. This is assuming that they're independent, right? So 0.2 times 0.5, or 2/10 times 5/10, 0.1, right? Yeah. So those were assuming it was independent. So independence means that one does not impact the other. So events A and B are independent if and only if the probability of A is the same as the probability of A given B. The probability of some event happening given that some other event has already happened. So another way to think about it, or this is the same thing as the probability of B is equal to the probability of B given A, right? So notice what's happening here. So like me having another event happen before it, right, does not impact the probability of the next one happening, right? So the probability of A times the probability of B is equal to the probability of A and B. And we kind of closed out the last lesson with one question about independence, and we used this concept. Conditional probability is this idea of givens, right? So these right here are conditional. Like we're putting a condition in place that's maybe changing the, like what we're looking at, right? Like our total, our focus isn't maybe on the entire situation anymore. Like this is saying like the probability of A happening out of everything. This is saying, well, now B has happened. What's the chances A happens? Does that affect it, right? So like you're narrowing your focus to saying something's already happened. So there's a condition, right? So that's conditional probability. So if an event B depends on event A, then the probability of A given B is equal to the probability of them both happening over the probability of B, right? And so this, I like to picture, it's a Venn diagram saying, well, the probability of me being in, let's say, you're narrow, right? So if this is A, this is B. So the probability of B happening is going to be, well, I've narrowed my focus to here. So now just in here, what's the probability? Like, I don't care. Like you're zooming in. Well, that's going to be this, right? So this part over the entirety of it, right? That's the chances now. It's like my total is not the whole picture anymore, right? It's not all of this. I've just focused in on that circle. It's saying like I'm zooming in, right? And now that I'm just looking at this because this happened, I'm in this location. What is the probability I get in here, right? What's the probability that I'm also in A? And that's got to be their intersection at this point, right? So the probability of A given B is the probability, let's take a look at this. The probability that it's a football, given that it's already a volleyball. Narrow your focus. So, oh no, these didn't animate? Darn. It's okay. Just pretend that they did. Pretend you can't see them. So now we're gonna take a look at some marbles. So we have 5 blue marbles and 7 green marbles, and they're in a bag. So these are going to be dependent, right? One's going to depend on the other. Once I pick one out, my total is less. So choosing 2 blue marbles without replacement. That's why this sum goes down. We looked at some stuff that had no replacement with the chocolates that Mr. Getz gave Miss Getz, right? So choosing 2 blue marbles without replacement. So the first one, I have a 5/12 chance, and then I have a 4/12 chance, right? And I'm going to use the multiplication principle. The probability of 2 blue marbles is choosing 2 blue marbles over the number of ways to choose 2 blue marbles. I'm sorry, to choose 2 marbles. Oh my goodness, that shouldn't be B. Sorry, guys. This is B. And this is C. The probability of 2 marbles. So let's like take this back to combinations. You're going to pretend that there's going to be a big reveal down here, even though you can see it. Choosing 2 blue marbles. The probability of choosing 2 blue marbles. Well, 5 choose 2. Like how many different ways out of those 5? Whoa, combinations, right? How many ways can that happen? Over how many ways total could I have picked 2 blue marbles? That's what's happening here, right? 5 choose 2 over 12 choose 2. You know how to do this. 5 factorial over 3 factorial, 2 factorial. You can probably come up with that, right? 5 times 4 divided by 2, what is that? 10 over 12 factorial over 10 factorial, 2 factorial. What is that? 66? 10 over 66? What was this? 20 over 132, right? Isn't that what 12 times 11 is? Oh, they're equivalent, right? 5 over 33, right? Because you're choosing things. You can use combinations. What about choosing 2 blue marbles? And I'll explain what all of this is because you obviously haven't looked at it yet, right? Choosing 2 marbles, one that's blue and one that's green, without replacement in any order. And that's a really key piece of it here, the in any order. That's where this is coming from. I think something animates. They're dependent. There you go. There's the animation. 2 factorial. That's the any order piece, right? I don't, and think about how multiplication works, right? This could be 5 over 12 times 7 over 11, or 7 over 12 times 5 over 11. That's not going to change anything, right? I can swap these numerators. Multiplication can happen in any order. So that 2 factorial accounts for how many orders that this can happen in, right? There's 2 factorial ways that this could have happened. I could have done 5 over 12 times 7 over 12, or I could have done 7 over 12 times 5 over 11. Okay, so that's what that 2 factorial is doing for us. It's like when we were putting like names, and it was like, how many different ways can you order these letters? How many different ways could you order these fractions? Or could you order the numerator, I guess is what I would go with. So I also want to then take a look at this. Well, I could represent it as combinations, right? Let's see, I'm going to go with the blue. I'm choosing one blue. 5, choose 1, 7, choose 1, over 12, choose 2, right? This is the total combinations. This is the probability of picking a blue times the probability of picking a green over, I'm sorry, the number of ways you can pick a blue, the number of ways you can pick a green, and then the total number of ways that you can pick 2. We could do that. I don't know if 5 factorial over 4 factorial, 1 factorial, times 7 factorial over 1 factorial, 6 factorial, 1 factorial, over 12 factorial, 4 factorial over 10 factorial, 2 factorial. Well, if we did that one, right, it's 66. There's 66 ways to get 2 marbles. We already did that. And this is going to give me just 5, right? Whoa. This is going to give me just 7, isn't it? So 35 over 66. That's the 2 factorial will take care of it, right? When I do 12 times 11, I obviously get 132. Well, if I have a 2 factorial at the top, 35 times 2 factorial, which is 2, over that 132, well, I got 66. Pretty cool, right? And then down here, choosing 4 marbles. 4 now, I'm no longer picking 2, so things are going to change a little. So here's what's happening here. I pick 4 marbles without replacement and in any order. Again, keywords there. Let's think about, we had a 2 factorial here. Here it looks a little different. What does this mean? Let's think. So I get a blue, and then I get another blue, and then I get a green, and I get another green, right? So this is assuming it happens in this order, right? I want to figure out how many ways could I have ordered these 4. Okay, so how many ways could I have ordered them? 4 factorial. But just like when we did names and letters repeated, the colors repeat. So I have to account for the fact that I don't care if it went, like I'm going to have orders in there where it went blue, blue, and then the blues switched and it looked exactly like it looks the same to us. So we want to account for those. And so this is for the repeating blues. Oh, goodness, I'm having some trouble. Oh, no, I zoomed in. Just like conditional probability. How do I zoom out, though? Oh, gosh. I'm not sure if I did that correctly. Ah! Make it stop. I shouldn't try it again, right? I should just rewrite it. 4 factorial. Okay, I lost my train of thought now. So the repeating blues and the repeating greens is where this is coming from. Okay. So I could also write this as combinations, right? And so maybe I would write it as, now I'm going to be picking 2. So I would have 5, choose 2, 5, 7, choose 2, over, and I'm picking 4, 12, choose 4, right? Oh, I wrote it in a different notation. Sorry about that. Combinations. Look at that. Okay, so inclusive probability. The probability of events A or B occurring is the probability. We did some work with this, right? We did this. We just didn't refer to it as this. The probability of A union B. You can picture a Venn diagram too, right? So here's my Venn diagram. The union is all of it. It's A or B happening, right? That's what this kind of means. A union B, A or B. Either one of them happening. So, and this is actually really good that I have this picture here. So it's the probability of A plus the probability of B minus their intersection. Well, why might I be subtracting their intersection? And we did one where this kind of came up. So let's see. The reason I'm going to subtract it is if I just took the probability of A, I'll use my highlighter. Let's say this was A, and I took that. And then I added to it the probability of B. Well, I just highlighted something twice. I highlighted their intersection twice. So I'm double counting, which is why I need to subtract one of them. Right? If they're like not, if they've got nothing in common, if they have no overlap, that would just be 0. And we would be able to just add them together, which we've done in the past. Right? You guys have seen some of that happen. Oh, that's a poor color to highlight. Think of Venn diagrams. What is the probability of drawing a heart or a jack? So you're like, look for keywords, or out of a standard deck. That's 52 cards. Right, so the probability of getting a heart and a jack, or a jack, one or the other is the probability of getting a heart plus the probability of getting a jack minus the probability of getting a heart and a jack. So let's think through that. What's the probability of getting a heart? Isn't that 1/4? What's the probability of getting a jack? I think there's 4 jacks out of 52, so that's 1/13. So maybe I should leave these out of 32. I'm sorry, out of 52. 52. Probability of getting a jack would be, I lost my train of thought again, 4 out of 52. Minus, how many jack hearts are there? Oh, 1. Right, there is an overlap. Something would be double counted. There's one card that exists in both of these sets. So that would give me 13, 17, 16 out of 52. Right, or what is that? 52, 26, 8 out of 26, 4 out of 4 13s. Right? Yeah. Okay. So after Hurricane Katrina relief, 200 people were surveyed in a community. 65 said they donated food. 50 said they donated money. 30 said they donated both. Right? So keep in mind that these 30 are included in these countings. Okay, so just remember that. A newspaper wants to figure out the percentage of people in the community who donated something. What percent of the people surveyed donated something? Right, and remember, 200 people total were surveyed. Sorry, here's the answer. There you go. So 65 plus 50, right? So this is the probability of food or money. This is the probability that they donated food plus the probability that they donated money minus the probability that they donated both food and money, right? Because they're double counted. They're already accounted for in these. So we don't want to double count them. They're being double counted, like they exist in these groups, in both of these groups. Okay. So we pictured these with Venn diagrams. Now let's take a look at these and let's do some picturing and draw this out with a tree diagram, right? To kind of guide our thinking. This allows us to see some conditions also, right? So it's another kind of pictorial like representation, and it really helps with visualizing the conditions, right? If something happens, what's the chances of something else happening idea? So let's see. So 2 identical cookie jars are on the counter. Jar A has 3 chocolate chip and 2 peanut butter. Jar B has 2 chocolate chip and 4 peanut butter. What's the probability of picking a chocolate chip cookie in general? So not from a specific jar. So let's see. I'm going to start over here, and we're gonna add some probabilities into this. So there are in jar A 5 cookies and in jar B 6 cookies. But the probability of picking jar A versus picking jar B, like those are equally likely, right? That's 0.5 or 1/2. Once I'm in jar A, the probability of picking a chocolate chip cookie, well, there's 3 out of 5. Probability of picking a peanut butter cookie, well, there's 2 out of 5. The probability of picking when you're in jar B, the probability of picking a chocolate chip cookie is going to be 2 out of 6. Probability of picking a peanut butter cookie is going to be 4 out of 6. Right? So like each of my like branches, my groups add to 1, which is neat. So let's see, I want to know what is the probability of picking jar A and a chocolate chip cookie. We know how to do that, the multiplication principle, right? So 1/2 times 3/5, 3/10. What about the probability of picking jar A and picking peanut butter? 1/2 times 2/5, 1/5. Well, I'll write it as 2/10 so we can see it better. The probability of picking jar B and a chocolate chip. The intersection of those two, right? 1/2 times 2/6, 1/6. I guess I didn't need to do that then. That's fine. The probability of B and peanut butter, 1/2 times 4/6. What is that? 1/3, 2/6? Let's see. What happens if I add all of these? And I took 3/10, added all of these possibilities, all of these outcomes. It goes to me what? 5/10, 1/2. And then this gives me 3/6, which is 1/2. And then I can add them, which, oh my gosh, that's 1. Neat, right? So those are all my possible outcomes, my probabilities of each of these events happening. So I want to know the probability of just picking a chocolate chip cookie. Well, I don't care which jar. Well, I'm going to take here, chocolate chip. Here, chocolate chip again. 1/6 and 3/10. And let's add them together. Let's combine those probabilities. Right? So let's see, what is that? 14/30. My math is not correct, is it? I multiplied that by I'm like, I did 6 times 5. Wasn't that 7/15? Yeah. Yeah, no, my math was right. 7/15. Right? You can find out a lot of other things. So this is not paying attention to a condition. I'm just saying, what's the probability of getting chocolate chip? Right? If I said, what's the probability of picking jar A? You could add these two. You don't need to because we could just look back here, but you could. I totally wrote over this, but so multiply along the branches to get those intersections and then add down to verify that it equals to 1. So I know I wrote behind here, but assuming you picked a chocolate chip cookie, assuming you picked it, so we know you picked a chocolate chip cookie. There's our condition. What is the probability it came from jar A? So the probability it's from jar A given that it's chocolate chip. That is a condition. Assuming that it is, we know that it's chocolate chip. That's what we know. So then how do I backtrack? I've got a chocolate chip cookie. That's my condition. How do I know which jar it's from? Or what's the probability that that cookie came from jar A? So this is the probability of A intersects C, the probability that it's both from A and a chocolate chip cookie over the probability that it's a chocolate chip, right? So the intersection, I have this. What does that say? 3/10, right? 3/10 over the probability that it's chocolate chip. We got that is 7/15. I want to rewrite it over here. 3/10. Let's multiply by the reciprocal. 15/7. So that's going to give me 9/14. Right? So the probability that it's from A, given that it's chocolate chip, is 9/14. Right? So just remember, like, pay close attention to what do we already know? Like, what is the condition? In this case, the condition was that it was chocolate chip. This would change if I said, what is the probability it's chocolate chip given that it's from A? My condition would be, or assuming that it's from A, what's the probability it's chocolate chip? My condition would be that it's from A. Okay. So throughout this lesson, we talked about the multiplication principle of probability. We looked at that and adding probabilities, right? So we looked at some the inclusive. As well as we looked closer, we definitely looked a lot closer at independence, figuring out if two events are independent in different ways that you can do that, right? And then conditional probability, these givens, and we took a look at some tree diagrams. So make sure that you are doing some practice with your textbook work, and we will see you at your next live session.